Alaikum, my name is Anis. So today I will be showing you the simulations of our program that was given to us. Okay, as you can see, this is our lab exam. So according to this exam, we have to design a line following robot that can perform these of the following five tasks. So let us read the task first. So first task is to integrate the three IR sensors on the proteus simulations. Okay, and then after that we have to add a climate control air conditioning system to sense the temperature of the environment using LM35. Then we have to control the speed of the motor using PWM, okay, using the DC motors. Then the robot should also have a hurdle detection. We should detect the obstacles and use the ADC sensor that can have a variable resistor. It's just the instruction. Sonar sensors can be used for the obstacle detection. After that, we have to use now two microcontrollers, one to integrate all the sensor and one to integrate the LCD, through which we will be sending our data through any serial communication that we have learned in the lab. So let me open my Proteus first. So as you can see the Proteus screen now. So over here I have integrated the IR sensors first, okay, and after that these are the two microcontrollers that are connected to each other as RXT and TXT to send and receive data transfer. So this is a liquid crystal display and this is also a LCD. Now you might be wondering why I'm using two LCDs. Well, through one LCD my data is being transferred and I'm just displaying my name on it and the roll number, and on this LCD I'm displaying all the other things that will be performing or that will be happening, like temperature, obstacle detection, distance, if my motor or my robot is turning right or moving straight or left. This is our temperature sensor LM35. This is the sonar that I'm using, and the potentiometer to change the obstacle distance. If I increase it, the distance should increase or decrease, just like that. And this is the motor driver that I'm using to control my motors, and you can see over here this is my left motor, or this is my left motor, and this is my right motor. And in these three IR sensors, the first sensor is the right sensor, the second one is the middle sensor, and the third one is the last sensor. Now as you can see over here, first of all I have VCC, which is the 5 watts that I am giving to all the sensor through the motor driver, and after that the ground is common for every component on this simulation. Over here you can see I have done the ground, and now similarly the pin connections are done according to the code. So while explaining the code I will show you how these pin connections are done. So first of all let me open my code screen. So this is the code for all the sensor integration, as you can see. So first of all what I have done is just include all the libraries of the Atmel Studio that I will be using, since I am using interrupt. So I include interrupt, delay, AVR, input output library, and this is the standard library that I am using. Similarly, after that I have just initialized some global variables. As you can see now, this global variable speed is actually initialized for the PWM to control the motor speed. So my motors will be operating on this speed, and this is an unsigned car. This variable is actually have been assigned as a global variable because I am using this variable to send and receive data to the other microcontroller through UART communication. So first of all I have declared the UART functions. As you can see that first of all I have set the UCS R0B registered, which is actually used to enable the transmission and the receiver of enable transmission and receiver, receiver of the microcontroller. As you can see over here, this logic is used to turn on the receiver, and this is used to turn on the transmission of the microcontroller. And then after that, UCSR0C is the register that is actually used to set the data mode of the UART. So I'm using 8-bit data mode over here. Okay, so this is on the UART datasheet, and UBR R0 is actually the port rate that we will be using. Let me show you first over here. As you can see, we are in UART. So right now in UART you can see that these are the main register that we will be using, or that are needed to perform the serial communication with the help of the UART. So the register that we wanted to see was over here UCSC01. As you can see over here, I was using 8-bit mode, so since the UCSZ01 should be 1 and UCSCZ00 should be 1 too. So over here you can see I have assigned them 1 1, so my mode is 8-bit mode. Now after that, I have created a function to send a data to the other microcontroller through the transmission pin of the first microcontroller of the sensor. For that, I have just used an argument unsigned car p. Okay, now over here, this condition is actually checking if my register UCSR0A and UDR0E is actually to send and to transmit data to the other microcontroller. If this my condition is true or not. If this my condition is not true, okay, then my loop will not execute it. If it's false, so it will complement it, it will become true, and then my UDR register will be equal to the any value that I have assigned to this variable. And then there is just a specific delay of 25 milliseconds that I have given on my own reason, because first, when I didn't add this delay, then my microcontroller was not working properly, like it was displaying data on screen continuously and erasing it. It was so fast that we couldn't see it. So let me show you UDR0 function. Register first. So I just took this logic from over here. It is actually used to set the parity bit. Okay, oh, wait until the UDR is 0, and when it's become empty, then our logic will be set. Now move towards code. uh, as you can see over here, then I have make a function to send string. Actually, we know that in UART we cannot send numbers, okay, or integer values, so we need to send some string or some char value. So for that, I have made this function. Actually, what is happening in this function, I have assigned a pointer. Okay, now in pointer, always the address of the variable is stored. So for that, first I am checking that if my pointer address is 0 or not. If it's not equal to 0, then what will happen, it will send data to the other microcontroller, and the other microcontroller receiver will receive that data, and then I am just incrementing p and giving a random delay according to my own choice. So now moving towards our first task, which was to integrate 3 IR sensors. As you can see on the screen right now, this is the function that I have made for the integration of the 3 IR sensor, and based on the logic table that I have made in the report, let me show you first. Okay, this is the logic table according to which my sensor will be working, and I have calibrated them according to this logic design. So first, if my right sensor will be 0, middle sensor will be 0, left sensor will be 0, then my motors will be stopped. Okay, and the hex value, I'm using the hex value because I have used a switch case statement, and then I am assigning each case a hex value for the different combination, because decimal value of 0x00 is 000. That's right. So if my right sensor is 0, middle sensor is 0, and left sensor is 1, then my right motor will turn on. Okay. And similarly, if my right sensor is 0 and middle sensor is on the black path, so it will give us one value, and the left sensor is 0, then my both motor wheels turn on and my robot will move in the straight direction. And if my right sensor is 0, middle sensor is 1, and the left sensor is also 1, then my robot will move in the right direction. Okay. And if my right sensor is 1 and middle sensor is 0 and the left sensor is also 0, then my robot will move in the right direction. Actually there is a change. For this it will go in right, and for this it will go in left direction. Okay. Similarly, over here it will go in left direction, not in right, because my left sensor is 1, and I have just a little mistake in writing. I'm glad that I was able to correct it while the video recording. And similarly, if my right sensor is 1, middle sensor is 0, and the left sensor is also 1, then it will also move in the straight directions. We don't need to turn at that time. Okay. And if my right sensor is 1, middle sensor is 1, then it will turn on the right motor and will turn in the right direction, not in the left. Okay, now if all of my sensors are 1, then it will stop over there. It means that it's our stop point. So this logic was designed according to our path that was designed on campus to perform our project. So similarly, I have used this logic table to implement my logic. So over here, as you can see, for the IR sensor, what I have just do is first we will move towards the main body of the program. Okay. uh, this is the main body of the program. As you can see over here, these are the two lines that I have used to initialize the input and output pins for the IFS. As you can see on DDRP, on the pin PB2, PB1 and PB0, I have initialized my sensor. Okay. So now we will move towards the proteus, so I can show you. As you can see on the right sensor output is O1, the middle sensor output is O2, and the left sensor output is O3. So I have assigned these output to PB1, PB2 and PB0. As you can see, PB0, O1, PB1, O2, PB2, O3. Now after that, now DDRD, actually it is used to initialize the output ports of the port D, PB, PD7, PD6, PD5, PD4. These are actually used to control the motor through the motor driver. As you can see, PD4, IN4, PD5, IN3, PD6, IN2, PD7, IN1. Okay, these are the pins that are used to drive the motor and control the directions of the motor. Either the motor will rotate in clockwise direction or anti-clockwise direction. As you can see, IN1, IN2, IN3, IN4. So now I will move backward code and I will explain you the IR sensor code first. So this is the IR sensor function. I have just assigned a uh, variable of car type q is equal to 0. I'm just declaring a variable, then I'm just comparing this variable with the value on the pin B. Actually this is the value that my sensor will be reading as an input from the environment when they will be detecting path, and then we are just comparing that value with the 0x07 the hexa value. As you can see, there were total combinations on the report on the logic table. As you can see, it was 0x07 the highest value. So I am just doing the AND combination with it, because according to that, when I will do the AND combination with it, the any value that my sensor will be reading just will come under this these conditions, and my motor will operate according to these conditions. So first of all, I have applied a switch case statement. So the case 004, as you can see, in the case 004, my motor will move into the right direction. So first I have, this is the PMW function to control the speed of the motor, and this is the speed variable that I have declared upward. As you can see, it has a value of 462. So my motors will be rotating at the RPM of more 462. They will have that much speed. And then after that, this is for the right motor. Okay, and now as you can see, after on the port D0X08, then the it will be displaying that turning left, because we will be uh, so as you can see, I was just explaining this part of the code. So in the case 01 was that our robot will move in the right direction, so our right motor will turn on, left motor will stay off, and then on port D, the this value will send to rotate our motor clockwise, and this will be displayed on the LCD like that our motor is right moving to the right. Okay, yeah, turning right. And similarly in case 02, you can see, oh, I have missed one case of the right. Oh, so the case 06 was also the right case. So if my middle sensor and the right sensor will give us one value, so my right motor will turn on. Okay, and then the same case will happen, my robot will move in the right direction. And the case 02 was the straight case, in which when my middle sensor, okay, the case 02 in which my middle sensor reads one value and both of the other sensor, left and right sensor, are zero, so my robot will move in the straight direction. That's why both of the motor will turn on. Okay, and it will move in the straight direction, and it will display move straight in on the LCD by some delay of 10 milliseconds. And similarly in case 05, my middle sensor was 0 and my both of the left and right sensor were 1. So in this case my robot will still move in the straight direction. This, as I told you, this logic was designed according to the path given us, according to the path given to us on the on campus, okay, for our project. So as you can see in on case 07, my left sense, all the sensor will be 1, so it is a stop case. Both of my motors will be 0, no value will be given to them. And similarly it will display stop on the LCD screen. Now in the case 00, when all the sensors are reading no value, in that case my motors will be still stop, they will not move. I will implement this logic on the Proteus 2 and you will see my simulation will be working perfectly. Now the case 01 was when my left sensor will read a value. So my over here the right motor will be 0 and the left motor should have the speed. So the my left motor will turn on and it will display turning left. Okay, and similarly in the case 03, you can see that my middle sensor and left sensor are reading values, so my robot will move in the left direction. And similarly over here I have to make this change. I guess I have missed it by some mistake, but it's good that I did saw it. Okay, so now I will just build this solution, and now I will display I will show you the simulation if it's working perfectly or not. So let's stop the progress. Let us apply the first logic when all the sensors are 0, so it should display stop on the LCD. So all the sensors are 0, none of my motor should rotate. As you can see, no motor is rotating and it will display stop on the LCD. Actually my Proteus is a little bit slow, so that's why it's taking a little bit time, but it will display, as you can see, STOP, stop. It's displaying stop. So our next logic was that when left sensor is 1, it should turn into the left direction. So left sensor is 1, we'll simulate it. Now we have to wait a little while. So as you can see, it is now turning left because my left motor is moving, rotating, so my robot will move in the left. So actually, my sensor motors were not working properly. Actually, when left sensor was on, it was showing the that turning right. So actually, I just saw that I have not named the pins in the order. So now you can see that we were on that. If left sensor is one, then it should show us that we are moving left. So as you can see, if I play the simulation, all right sensor and middle sensor are reading no values. So my left motor will turn on and it will display on the LCD that we are moving in the left direction. And this is my roll number 180925 and my name Khawaja. Okay, so it will show you turning left. Okay, now our next logic was that if our middle sensor is 1 and both of the left and right sensor are 0, so now my both of the motors will turn on and my robot will move in the straight direction. Now you can see moving straight. It will tell us now we are moving in the straight direction, and you can see both of my motors are actually rotating at the same speed at the same time, and they will achieve the speed of the 462 as I have set in the PWM. So now our next logic was if my right sensor is 1 and the middle two sensor are 0. Now you can see my right sensor are 1, the rest of the two sensor, middle sensor and left sensor are 0. Now it will display that turning right and my right motor will turn on. As you can see, my right motor turned on and it is displaying on the screen that we are turning in the right direction. So as far as my logic design is good and it's working, so now let's see the other one. Now if my right sensor was one, it is the now if my okay, right sensor and left sensor are 1 and the middle sensor is 0, then my robot should move in the straight direction and the both of the motors should turn on. So both of the motors will turn on. If both of the motors turn on, then it means that we are moving in the straight direction. As you can see, both of the motors turn on at the same time with the same speed, so we are moving in the straight direction. It is going to display that. Moving straight. So now our next logic was if my right sensor and middle sensor are 1, so we should move in the right direction. Okay, so we will turn the left sensor 0. Now as you can see that my left sensor is not detecting anything, but my right sensor and middle sensor detect some path, so it will move in the right direction. So my right motor got turned on, right motor turned on, so it will move in the right direction. So now the last one, if both all the sensor read 1, so it will be stop because that will be our stop point. This is our last logic. As you can see, my both of the sensor, all the sensor are reading 1. None of my motor got turned on, so it will display stop. So this is mean that it is our stop point. So now we will move toward code. Since I have explained the IR function, so I will just hide it now. The next function is actually the temperature sensor function. Actually, our first task was to integrate the IR sensor, okay, 3 IR sensor, and to make a logic design so that our robot will follow some path. And I have shown you its simulation. My simulations are working perfectly according to my logic table. So now the second task was to detect what is the temperature of the environment. So for that I'm using a temperature sensor LM35 as explained in our problem statement. So first of all, I have just initialized a variable z and a value. I have made a value array because we know that LM35, let me show you. Actually LM35, okay, you can see over here is a temperature sensor. It has three pins, okay, ground, analog or voltage output, and for the input voltage. Since this sensor give us an analog value, so we have to convert its analog output into the digital values. For that's why we use ADC for this sensor, which is analog digital converter. So we can convert an analog value into the digital value. For that purpose, first of all, I will move to the towards the main function. Okay, as you can see over here, I am choosing the port C as an input port because port C is mostly the analog port of the ATmega 328P, and I am integrating my analog sensor at PC5. Okay, so first of all, as you can see, to convert an log value into digital value, first we have to select the mux, okay, or the pin which we will be using, and okay, and for that purpose I have used this statement admux, which have we learned in the lab of the vgate. Yes, it was the analog digital converter lab in which we learned about how to integrate. As you can see, for that we have to use the mux channel, and which ADC5 I'm using that thing. So for that I have used this combination 1 RFS and mux 0 and mux 2. For that I will select a channel 85, okay, with an external capacitor FR pin. So now over here actually I am just enabling my analog to digital converter register, and then I have the interrupt. Okay, then the interrupt will activate it, and after that I am just selecting the mode of the clock. So I am just using 128 clock. Now let me show you how do I know that these register are used for specific selection. As you can see over here, I have used ADEN, ADIE, ADPS0, ADPS1, ADPS2. So as you can see, ADIE is actually used for the interrupt enable. So since I am using a temperature sensor, I am enabling its interrupt, so I can convert its analog value into the digital value. Okay, and after that I was using ADEN. As you can see, ADEN is actually analog to digital converter enable. So when we enable this register, our value will start converting into the analog value. Okay, after that my interrupt flag was activated, and after that I select the mode, the clock mode, which was 128. So crystal, I have used the 128 frequency. As you can see, to select the clock of 128, my ADPS2, ADPS1, ADPS0 should be 111. So as you can see in the logic, I have set them as 1 high, high, high. So my clock will be 128. Now I will move toward the function, and you will be able to understand it better. Now, as you can see over here, we have seen that I am just setting my ADSC register, which is used to start enable the analog to digital conversion. So over here my analog digital conversion will start. Now this is the condition where I am checking that if my ADIF register, which is actually as an interrupt flag, if my interrupt flag is set high, because when my interrupt flag will set high, after that my ADC conversion will stop until we reset that flag. So we are just comparing it with ADCSRA register, which will set it to the 0. Okay, over here as you can see we are setting it to 0, so it will keep on converting my as long as the sensor will keep on reading the value of the temperature. Okay, now after that I have just cleared the ADIF flag, and now over here actually the variable that I have declared, I am storing the value in it. So actually these are the register which contains the analog value. So in order to convert it, I have multiplied it 5 and divided by 1023. Now the reason I have divided it with 5 is actually our ATmega 328P operates at 5 voltage, and it reads only from 0 to 1023 analog value. So I have to divide it by 1023 in order to get the digital value and multiply by 800. So now ITO is ITOA is actually a special function which is used to convert the integer value into the ASCII. It is a standard library function. That's why I have included a standard library in it. Now, after that, I'm just setting LCD cursor and then displaying the value on the LCD, and then that this is the temperature. I will show you this simulation to end delay. Over here, I'm sending that data to the to the other microcontroller. Over there, the data will be received by the RXT and it will be displaying on the screen. So let me show you the simulation of the temperature sensor first. Over here you can see that first of all, actually the IR sensor simulation will run, because in the main body of the loop, first of all IR sensor is being called and then the temperature sensor. So we have now it is showing us the temperature. As you can see, my temperature sensor is set on the 27, so it is telling us that the temperature is 27 Celsius. Now I will stop and I will change it to the 30. Okay, now it will display on the screen that now our temperature is 30. So first it will display that no motor is working, so we are in stop state, we are not moving, and then it will tell us the temperature, because after that I have called the temperature function. Now as you can see, it is telling us that now the temperature is 30 Celsius. So that means that my temperature sensor code is working perfectly and well. Now I will move towards the okay, now the PMW task. Actually, PMW is the pulse width modulation. This is used to control the speed of the motor. As we know that Arduino 80 mega 328p operates on 5 watts. Okay, now the it cannot give the constant supply of the voltage at each pin. The voltage keeps on varying from 0 to 5. So in order to maintain the constant value of the voltage, we use pulse width modulation. So actually we can say that it's like over here in my code, I have written about it, so you will get a better idea. So actually it is used to control the voltage from the pins of the Arduino, since we are interfacing the motor driver. Okay, so that's why we need to supply a constant voltage to the motor, so they will have a constant speed, so the speed of the two motors will not vary. So actually in order to operate the pulse width modulation, we have to use timer. Okay, now we know that 80 mega 328p has three built-in timers. So over here I'm using the timer 2 and timer 0. So first of all, actually I'm just initializing the over here I'm just initializing the timer for the right motor, and I have selected the timer 0. As you can see, we know that in a timer 0 there is a register called TCCR0A, which is used to select the mode of the timer. Okay, over here the mode that I have selected for the timer is the fast PMW mode, and TTCRB is actually used to select the mode of the clock. So I have just select the normal clock, no pre-scaling. Okay, normal mode of the clock. So now moving towards the left motor timer. Now for the left motor I have used the timer 2. We can use timer 1 also, but I have used the timer 2. Similarly, first I have set the register TCCR2A to as a fast PWM mode, because I am actually controlling the speed of the motor and I need to control it by PWM pulse width modulation. So I have set that mode of the timer as a pulse width modulation mode, and then similarly I have set the clock as a normal clock, no pre-scaling, because TCCR2B is actually a register which is used to select the clock mode of the timers. Okay, now we will move towards the duty cycle of the right motor. Now actually the duty cycles tell us Actually, OCCR0A is a register which is used to compare the value. Okay, now the duty cycle is something that tells us that if our wave is, let me explain you on a notepad, but I don't have any notepad. So let's move towards Word and let's see if I can explain you over here by drawing some wave. Okay, so okay, now suppose that this is a wave. Okay, it is turned on for just a specific interval of time. So actually what we will do is actually we will measure the time for which this wave was high and for which the time period for which this wave was low, and then we will divide that time period with some specific value that I have shown in the PWM section. Okay, we will divide the on time divided by on time plus the off time of the pulse. Okay, by that we will get the duty cycle. Now when we will get the duty cycle, we will just multiply it by 100 and multiply by 2 into 55, because our maximum value that our TCNT register of the timer can have is 0xff, which is 225. That's why we are multiplying it with 225 in the end. Okay, so now, and the similar case is for the left motor PWM, and it is for the timer 2, and we are doing it same for the left motor, and it will turn on and read the wave for how many or for which time interval or wave was turned on and for which time interval or wave was off, and after that it will calculate it, and then we will move towards the main loop. Over here I'm just initializing the timers for the both motors, left motor and right motor, and when this timer will be initialized, actually they will start counting. This timer will start counting that for up to how specific time interval or wave was high and or wave was low, and according to that they will calculate the duty cycle. As you can see, I have calculated it over here. This is where the calculation required, and this is the value that OCCR0A and OCCR2B will have, and this value will be compared with them in this function, uh, in the function which was the duty cycle function. As you can see over here, that value is being compared over here. Okay, now since I have used uh, this PWM in the IR sensors to control the speed of the motor. Okay, now first, after initializing the timers before calling the IR sensor functions, the timer will be turned on and they will keep on calculating the time for which specific interval or pulse was high and or pulse was low, and they will calculate the duty cycle, and after calculating the duty cycle they will compare that value with our speed. And if okay, and then they will, when they will compare our value with the speed, and then they will assign that speed to the motor. As you can see over here in the right motor function, I use that value should be assigned to the motor, and our speed was 241. So after that value will be, never mind the disturbance, it was someone, that's why I stopped for a while. So where was I? On the IR sensor. Yeah, so actually the when our value will be compared, then it will be assigned to our right motor, and that will be the speed of the right motor. So in order to check the PWM, I will show you my simulation that it's working perfectly. As you can see, the speed is 462. I have set it as that. Now I will just turn on the both motors so you can see that it is working perfectly. and I will just run the simulations. Now both of the motors will turn on at the same time and they will have same speed at the same time, and they will reach the speed of 462 because I have set their speed to the 462, and they will not achieve any other speed because that's what pulse width modulation is used. So it will take a time for them to achieve that speed. So up to that, until that, we just move towards the ultrasonic sensor. So now this is was the our fourth task, to integrate an ultrasonic sensor that will use to detect an obstacle. Now since we know that ultrasonic sensor actually we know that ultrasonic sensor is has a trigger and an echo. The trigger is used to generate ultrasonic waves, and echo receive those ultrasonic waves when they are being bounced back by some obstacle placed in front of them. Okay, so I will move towards my report and will show you about the ultrasonic sensor and the formula that we are using. So this is an ultrasonic sensor. This is the pin configuration of the ultrasonic sensor. As you can see, okay, it has four pins. One pin is for voltage, the other pin is for trigger, which is an input pin, then echo pin, which is an output pin, and the ground pin. So now I will move towards my code, but before that we will just wait. As you can see, my motors are going to achieve the speed of 462. It's already 450 their speed. It will be 462. So soon, at that time I just explain you the code of the ultrasonic sensor. First of all, I have just declared some variables and make an array to store the value that will be kept on reading by the echo of the ultrasonic sensor. Let's move towards the main function. So as we can see that we have to generate the ultrasonic wave for the specific interval of time, because when we generate a wave of the ultrasonic sensor, it just creates the sonic cycles. Okay, these sonic cycles goes in the air and then they collide with the obstacle placed in front of them, and then they bounce back and then the echo receive it. So first of all, I'm just setting my interrupt. Okay, this is the interrupt logic which is used to set the mode of the interrupt. Let me show you over here. The lab 7 was about the interrupt. So as you can see, IECS01 and ICS00, these are used to select the modes of the interrupt. Since I am using ICS00 as a 1 and 10 mode, so my is the falling edge. So okay, my interrupts will be reading the value during the falling edge of the waves. So by now the speed of the motors will be 162. As you can see, it's 161. So it will be 162 soon, and it will stay 162 and it will not increase. Okay, simulation log. Okay, just be 160. They will be 162. So it's actually my laptop is just taking a lot of time, that's why. So now over here, this is the register that is used to enable the interrupt, and since I am using the INT0, so the external interrupt will be enabled. This is using to enable an external interrupt. So now with the help of that external interrupt, I will be able to control my timer, and I will able to control the wave for which specific time interval my wave will be generated, and after that I will use the formula to calculate the distance of the obstacle, and I will explain. So over here I have just made a condition in which I am just turning on my counter. Okay, it will start reading the time. I have set it is mode as CS10. As you can see that in timer, CS10 was a mode which is used for the uh, as a normal mode with no pre-scaling of the clock. So it will start the counter with no pre-scaling. The clock will start and with it will keep on reading, and then after some time interval I just set it to stop. Now my TCCR2B timer 2 register 2 will stop counting, and it will store the value that it has count to the wave variable that I have made now, and then it will set the TC and T2 register 0, so we can use it again. Okay, and it will keep on telling us the distance again and again. If we will not set it at 0 value, then for the next time it may not give us the proper actual distance at which obstacle is placed. So now over here I'm just using the formula to calculate the distance. Now the wave is multiplied by with the speed of sound. Actually the speed of sound is, we all know that the speed of sound in air is actually it was, I forgot, but I have multiplied it with the hexa value of that. It was mm, 3 something. Let's see the, okay. I will tell you what was it. I will just perform it. 0x154. Okay, now the speed of the sound in is air is actually 340 meter per second. Okay, now this is the hexa value of the speed of the sound. I have multiplied by its wave, and then I have divided by 8,000, negative 1000, because my sensor was actually giving me a negative value of the negative value. Okay, and it was giving me in the millimeters, so 1 centimeter is equal to 1000 millimeters. That is why I have divided by 1000 to get the reading in the centimeters, and then after that I am just using the same function to convert the integer value into the ASCII, so I can send that value to the other microcontroller and it will be displayed on the screen LCD. And then after that I am just setting the cursor and then displaying it on the LCD, displaying the value in the centimeter, and then the delay, and then clearing the LCD. Sorry about if I got stuck over here. Actually I forgot what the value was, so it's actually 340. This is the speed of the sound in air. So I have written its hexa value. Since I am using hexa value, hexadecimal value, I have used it in the IR sensors case too. That's why I have written it in the hexadecimal. So up to now my speed of this, as you can see, this is the speed of the sensor motors. It will remain 462. It will not increase, since because I have set the pulse width modulation speed up to 462, so my motors will keep on rotating at the speed of 462. So this is what the this was our fourth task. Now this is the main body of the loop. As you can see over here, I have used these lines. Okay, this line is used to declare the pins for the motor driver as an output, and DDRB is declared as output. These are the 3 pins of the sensors, and this is the pin of the ultrasonic trigger pin, which is declared as an output, and this is the ultrasonic echo pin, which is declared as an input. And then I have set the whole port C as an input port, because my LCD, one of my LCD is also connected to the C port, and in the library of the, as you can see in the library, as you can see, I have connected the data pins of the LCD with the port C, and that's why I have declared the whole port C as input port. So now after that it will start conversion of the analog to digital converter, which I did explain to you, and then it will set the interrupts for ultrasonic wave, and then in this loop it will keep on calling this function again and again, and their value will keep kept on displaying to us on the screen. Now I will show you first the ultrasonic simulation, but before that I will show you the code through which I am sending data to the other LCD, which is the UART case. As you can see in this code, I am using the port. I have, first of all, I have set the pin 0 as an input pin because it is our receiving pin over here. It is connected to the transmission pin of the other of the sensor integrated microcontroller, and similarly DDR B as an output because I have connected my LCD with it to display data on it. And this is the baud rate that we have calculated in UART. Over here, as in my report, you can see I have performed some calculations. So my baud rate was calculated. Actually, this baud rate was the baud rate you gave to us uh, in the sixth lab over here in the examples of the program. So I used the same baud rate and the same conditions from here. Okay, I just picked it up and just paste it over there after understanding it what they meant and what they do. So after that, I have set the register and assigned it a unsigned car value, which is the UBR baud rate, and setting the UBR register of over here. Actually, in this I am setting the higher bits of the UBR, because UBRR0H in UART is used to set the higher bits of the UBRR, and UBRR0L is used to set the lower bits of the UBRR register. Okay, now after that, what I am just enabling the transmission and the receiver of the other microcontroller to which my LCD is attached. Of this microcontroller, I am enabling the transmission and the receiver pin. And after that, what I am doing is actually is selecting the data of the bits which will be character size on the screen. What will be the character size on the screen? As you can see over here, uh, UPCSZ02, UPSC01 actually is used to select the character size that will be displayed on the screen. So the character size that I am using is actually UPS0 is 1 and UPSC00 is 1. So my character size is actually 1 bit, okay, or 3 bit. So it will be displaying data on the screen according to that. Now after that, I have just created a variable which will be receiving the values from the other microcontroller, and I have named it as accepting. Now this is a forever loop, and I'm just displaying my name on the LCD first. And over here, this is the condition. It will just wait until my register my receiver of the microcontroller gets empty, because once my receiver will start receiving data from the other microcontroller, then it will kept on receiving until that microcontroller stops sending it data. So when it will stop, then we compare it with the UCSR0A to check whether my this register receiving register is receiving any value anymore or not. When it will not be removing or receiving any more value, then it will assign the value that we have received from the other microcontroller to the variable that I have created, name accepting. And then after that, on that accepting, I have just made some condition of if else, that if my data that I have received, which was stored in UDR0 and that was assigned to the accepting, is 0, then display this on the screen, otherwise display also this on the screen. I have just done this to show my name on the screen. That's why you can see I have displayed my roll number and my name. So this was my code. Okay, it's already built, and I will just show you now the simulation once properly. Okay, now this is the simulation. My both motors will turn on since my logic is 101, and it will display that moving straight. And since the temperature is 30 right now, I will change it to 29. Let's see if our temperature changes or not. And I have to show you the ultrasonic simulation too, so I will show you the ultrasonic simulation at the same time too. So now it's moving straight, and this is my name and roll number. And now this is the temperature 29. As you can see, it's 29, so it's telling us the temperature is 29 Celsius. And now it will tell us the distance of the obstacle. Now the distance of obstacle is 21 centimeters. So obstacle is 21 centimeter away from us. Now I will change the value on the potentiometer. Now let's see if the value of our obstacle increases or decreases. And let's change the value of the temperature to 28 and let's see if it will show us 28 or not. Since my both motors are moving and they will achieve the speed of 462 due to the PWM pulse width modulation. Sorry about if my simulations are taking a lot of time because my laptop is really slow right now. I didn't shut it down for like 3 days. So now the distance is 25. As you can see, first our distance was 24 because the resistance was increased, so the distance was less. As the resistance decreases, the obstacle got away from our robot. So these were the simulations and they're working well. I hope you all understood my code very well, and if there is any query or question you can ask me freely, and I will stop recording now.